Hello and welcome to this 8th and last module of our introductory course to subatomic physics. In this 8th module, we will talk about two mysterious components of the universe, which are dark matter and dark energy. After following this video, you will know what we know about the Big Bang and what were the major steps in the history of the universe from its beginning up to today. Observations indicate that our universe was created some tens of billions of years ago in what is called a Big Bang and went through an extremely hot period afterwards. It then cooled down by expansion down to its current temperature of 2.7 Kelvin. Here you see a schematic representation of its evolution. The features of the cosmological standard model as we know it today are primarily based on the following observations. First of all, the systematic redshift of spectral lines from distant galaxies, which leads to Hubble's law. Second, the cosmic microwave background, which corresponds to that of a black body. The abundance of light elements in cosmic rays, and the distribution of large-scale structures, galaxies, clusters of galaxies, etc., and its relation to the anisotropies of the microwave radiation. We will walk you through some major steps of the history of the universe and review some of these phenomena as we go along. Extrapolation of the current universe backwards in time leads us to an infinite energy density concentrated in a single point. At the beginning there was thus a singularity, the Big Bang. You should not be afraid of singularities. They show up everywhere when we talk about volume density, when the volume tends to zero. The total energy of the universe was of course finite at t equal to 0 and the same as today for all we know. But the volume was extremely small. It has been constantly expanding ever since. Be careful not to trust your intuition when you think about the expansion of the universe. The idea that this is happening relative to a fixed system of reference is completely wrong. If you think about it like the explosion of a firecracker in the night sky, you're mistaken. It is space itself which expands. There is no way to observe this process from the outside. And the expansion concerns not only any distance between two objects, but any other length, such as the wavelength of photons, for example. Through this expansion, the temperature of the universe has decreased by the same mechanism that your fridge is using to cool down your vegetables. We can only speculate on the first few 10 to the minus 40 seconds of the life of the universe. In this era, the temperature was so high that all forces had the same strength, including gravitation. In addition, the dimensions were such that gravity had to work in a quantized way which we know nothing about. The homogeneity of the temperature in the universe indicates that diametrically opposite regions were in causal contact shortly after this era. This is not explicable unless it is assumed that around 10 to the minus 37 seconds after the Big Bang, the expansion of the universe passed through an exponential and superluminous phase. It is called a period of inflation. Its driving mechanism remains to be discovered. Again, we must not shy away from this thought. It is permissible by relativity that space itself expands at a velocity larger than the speed of light. Indeed, no signal exceeds this speed limit, including this era. It is space itself which is blowing up. After the end of the inflation period, the universe was filled with a plasma of quarks, gluons, and other elementary particles. The temperature was such that all particles were relativistic, particles and antiparticles were in thermal equilibrium. At some point during this era, a tiny asymmetry of unknown origin between matter and antimatter appeared. Matter became more abundant than antimatter by about 1 part in 30 million. The mechanism causing this unbalance, which is called baryogenesis, remains to be discovered. This mechanism is responsible for our existence. Without it, all matter would have annihilated with antimatter. The necessary conditions for this operation have been formulated for the first time by Andrei Sakharov. There are 3 such conditions. The first one is that C and Cp symmetry must be violated to objectively distinguish between matter and antimatter. The second condition is that baryon number must be violated so that antibaryons can disappear in favor of baryons. And third, all of this must happen outside thermodynamic equilibrium, e.g. In a phase transition, for example, so that antimatter is not recreated by the reverse process all the time. Beyond roughly 10 to the minus 11 seconds, we know a little more precisely what happened. In this era, the universe is sufficiently cooled down by expansion so that the laws of the Standard Model, which we have encountered in this course, are valid. The energies of the particles were then comparable to what accelerators can provide. Around 10 to the minus 6 seconds, quarks and gluons combined to form baryons. Before, this was not possible because the kinetic energy of the ingredients prevented bound states. The small excess of quarks caused a small excess of baryons over antibaryons. When the temperature was no longer sufficient to maintain the equilibrium between nucleons and antinucleons, a massive annihilation took place, leaving only about a single proton or neutron among 100 billion. A similar process followed at about 1 second for electrons and positrons, leaving a tiny fraction of electrons. A few minutes after the Big Bang, the temperature had lowered to some billion Kelvin. Neutrons and protons fused to form deuterium and helium, but most protons stayed on their own. At some point during this expansion cooling process, energy in the form of gravitational mass began to dominate over the energy of photons. After some 380,000 years, electrons formed atoms with protons and other nuclei. Before, the ambient photons were sufficiently energetic to ionize atoms when they formed. At this time, this was no longer the case. Photons and matter decoupled. Radiation released at that moment still exists today. It is called the cosmic microwave background. When all dimensions expand, the wavelength of photons also expands, and the corresponding temperature decreases. We call the residual radiation from that event the cosmic microwave background because its equivalent temperature today is 2.7 degrees. The wavelength is thus in the microwave range. This radiation therefore provides us with an instantaneous photograph of the state the universe was in 380,000 years after its birth. It is indeed the oldest source of light because before the universe was opaque, since photons were absorbed when ionizing atoms. By measuring the wavelength of the cosmic microwave photons, one can map the temperature of the universe. This was done first using ground-based microwave antennas, then with specialized satellites like COBE, WMAP, and most recently with the Planck satellite. The distribution of photon energy from any given direction exactly follows the one expected for an ideal black body. The characteristic temperatures are found to be homogeneous at the level of 1/100th of a per mil, even for diametrically opposite directions. This is the motivation for postulating the so-called inflationary era. However, there are indeed small fluctuations around the average temperature, which were caused by regions of slight over or under density. These are probably the seeds around which the large structures of matter that we observe today have formed. Since then, thus over the long period which lasts until today, gravitational attraction has caused matter to form gas clouds, then stars, galaxies, and galaxy clusters, and so on. The details of the structure formation depend on the type and quantity of matter available. Dark matter may have helped with this process, as we will see in video 8.2. Once stars are formed, elements heavier than helium are cooked by nuclear fusion, as we learned in module 2. If one takes stock of the observed components of the universe, one finds the following. The total density of matter deduced from the gravitational potential measured from the movement of stars in galaxies is of the order of 10 to the minus 27 kilogram per cubic meter. The total density of baryons, visible or invisible, both measured and deduced from the well-established baryogenesis process, is smaller by about a factor of 10. Visible matter, shining light, concentrated in stars, gas, and dust, is again less dense by a factor of 5. Most of the matter is thus neither visible nor baryonic. It is called dark matter. We will talk about it in the next video. The rest of the energy density of the universe is provided by an even more mysterious form. It is called dark energy and appears to be currently accelerating the expansion of the universe. We speak about the little that is known about it in video 8.3. But first we will discuss dark matter in the next video.